We had seen that in substitution reactions of alkyl halides, a nucleophile, such as hydroxide ion, replaced a leaving group, such as bromide, to give a substitution product. The reaction involved only the carbon atom bearing the leaving group. In contrast, elimination reaction follows the opposite pathway. Instead of nucleophile reacting with the carbon bearing the leaving group, base, hydroxide for example, instead abstracts the hydrogen from one of the alpha carbon atoms, and as the carbon hydrogen bond breaks at the alpha position, the two electrons serve to form the new pi bond between the alpha carbon and the carbon bearing the leaving group. In the late 19th century, Russian chemist Zaitsev had observed that elimination pathway under basic conditions in an alcoholic solvent had led to the predominantly product in which the new pi bond formed between the carbon bearing the leaving group and the more highly substituted alpha carbon. Let's take a look at the elimination pathway of HBr from 2-bromobutane. Leaving group is at carbon number 2, and we have two alpha hydrogen atoms. We have primary carbon at the alpha position with 3 alpha hydrogen atoms, and we have another alpha carbon, secondary carbon, with 2 hydrogen atoms. We see that the major product, had resulted from the elimination of one of the more acidic secondary hydrogen atoms. The minor product, 1-butene on the other hand, resulted from elimination of a hydrogen atom from the less highly substituted primary alpha position. Let's see what happened when the number of alpha hydrogen with the lesser degree of substitution was increased. Here we have 2-bromo, 2-methylbutane, with the leaving group bromine at carbon number 2. We have 3 alpha carbons, primary carbon with 3 primary alpha hydrogens, another primary carbon with 3 more alpha hydrogens, and we have secondary alpha carbon with 2 secondary, more highly substituted, more acidic hydrogen atoms. We see that under those conditions, when we doubled the number of primary alpha hydrogens, there was a slight increase in the ratio of the minor product. So if we compare 80 to 20 versus 70 to 30, we saw that with increased number of the less highly substituted hydrogen atoms, the major product formed less selectively. So still the major product has the pi bond between carbon number 2 and carbon number 3, implying that the more highly substituted hydrogen atom from the secondary position was eliminated, and the product can be designated as the Zaitsev, in this case tri-substituted alkene, because I have 1, 2, 3 non-hydrogen groups bonded to the alkene, versus non-Zaitsev product, which happens to be disubstituted alkene. Zaitsev way of elimination does not always hold for all elimination reactions. Let's take a look at the E2 reaction mechanism. E2, like SN2 reaction, is a one-step concerted process which doesn't involve formation of an intermediate, In this reaction, base abstracts the alpha hydrogen. The two electrons from the hydrogen-carbon bond collapse to form the new pi bond, and the leaving group X is expelled all in the same step. Transition state is somewhat crowded, and it involves partial bond between base and hydrogen atom, partially broken bond between alpha hydrogen and alpha carbon, partially formed pi bond, and partially broken bond between the carbon in question and the leaving group. Notice that the transition state involves anti-periplanar alignment between the hydrogen atom to be eliminated and the leaving group. Leaving group and the hydrogen atom have anti-periplanar arrangement. The alkene that forms, therefore, forms stereospecifically, and stereospecific reaction is one that involves a mechanism in which more than one stereochemical outcome is possible, and yet we observe formation of only one product and not the other. Taking a closer look at a transition state, again we see that the hydrogen and the leaving group are on the opposite plane, separated by 180-degree dihedral angle. Since both base and the leaving group in a rate determining step, and so one-step reaction, rate of the reaction that follows E2 pathway depends on the concentration of both the alkyl halide or tacrylate and the base. So bimolecular reaction kinetics, and we can, for example, say that if we double the concentration of the base, the rate will also double. If we double the concentration of the base and half the concentration of the alkyl halide, the reaction rate would remain unaffected. So reaction depends on the concentration of the base, nature of the leaving group, and therefore the better the leaving group, the greater the reaction rate. So we'll only consider chloride through tacrylate as the possible leaving groups for elimination reaction, and we will not consider strong conjugate bases of weak acids such as hydroxides, amide, and alkoxide. Such leaving groups would first have to be activated before they can be expelled as a leaving group. Let's take a closer look at the alignment of the leaving group and the hydrogen to be deprotonated from the alpha carbon. Newman projection shows that hydrogen that is anti-periplanar to the leaving group is the one that will be eliminated. In this example, we have 3 alpha hydrogens, 1, 2, and 3. And only one that is anti-periplanar allows for elimination. The look at the orbital overlap in a transition state explains why the anti-periplanar arrangement is necessary. As the base abstracts the hydrogen atom and the bond between alpha carbon and the hydrogen to be eliminated is being broken, the sp3 orbital will be rehybridized from sp3 to p orbital, because we know that the pi bond results from the sideways overlap of 2 unhybridized p orbitals. And the sp3 orbital involved in bonding, sigma bonding between alkyl halide carbon and the leaving group will be broken, and again this sp3 orbital will be rehybridized to the p orbital. So in order for the pi bond to form, sigma bond between the alpha carbon and the alkyl halide carbon will rotate until the 2 sp3 orbitals are parallel, meaning the 2 p orbitals will be perfectly aligned for the sideways overlap and formation of the pi bond. We will focus on elimination from substituted cyclohexanes. Let's take a look at the alkyl halide, cycloalkyl halide here with the chlorine as the leaving group at the tertiary carbon atom, carbon number 1. And we'll recognize E2 elimination conditions by looking at the strength or concentration of the base. E2 eliminations involve base that is stronger or more concentrated than 0.5 molar. So anything less than 0.5 molar will be considered diluted and will be more appropriate for the alternative elimination reaction, E1. Bases typically are alkoxide bases, conjugate bases of alcoholic solvent. So if we use ethanol as solvent, base would be sodium or potassium ethoxide with a little bit of heat. So again, strong or concentrated base, typically alkoxide, but hydroxide can also be used in alcoholic solvent with heat. Let's number the carbon atoms so that we can keep track of them as we draw the chair conformation of the cyclohexane. So I numbered them 1 through 6, starting with the carbon bearing the leaving group. And again, we're just numbering these carbon atoms for purpose of keeping track and not for naming the compound. My initial chair conformation, I have chlorine at carbon number 1. Since chlorine is attached via hashed bond, it means that it is pointing down. Alkyl group, the methyl group, is pointing up. Carbon number 2 has a methyl group pointing down, which happens to be axial in chair conformation. Carbon number 5 has a methyl group pointing down, and therefore hydrogen is axial and up. And carbon number 6 is unsubstituted. So once you draw the chair conformation, firstly, look at the leaving group. In order to consider E2 elimination, the leaving group, in our case chloro group, has to be in axial position. If it is not, do not even consider what product you will form. You need to flip the chair until the leaving group is axial. So here from equatorial, I flip the ring until chloride group is in axial position, and only then I will look at my alpha carbons. So again, chlorine is at carbon number 1 pointing down, methyl group is up and equatorial. Carbon number 2 has methyl group pointing down, therefore hydrogen is up and axial. Carbons 3 and 4 are unsubstituted. Carbon number 5 has methyl group pointing down, and therefore hydrogen is up and equatorial. Circle the leaving group, double check that it indeed occupies axial position, which it does, and then draw the hydrogen atoms at both alpha carbons. My alpha carbons are carbon number 2, and I already have a hydrogen there, and carbon number 6. Carbon number 6 has axial hydrogen and equatorial hydrogen. Since both pathways to elimination of hydrogen from C2 and C6 are possible, in this case, I'll compare degree of substitution to decide which hydrogen atom is more acidic. Because when you have more than one alpha hydrogen, in that case, once you confirm that the leaving group and the hydrogen that you consider for elimination are axial and antiperiplanar, the Zaitsev rule will be followed. And the hydrogen that will be eliminated is the one that's more highly substituted. Therefore, I am looking at tertiary hydrogen atom versus secondary hydrogen atom. Both of them are axial. In this case, base will abstract the more highly substituted tertiary hydrogen. Sigma bond between that hydrogen and the alpha carbon will break, and 2 electrons from this bond will go to form the pi bond between carbons 1 and 2. Leaving group will be expelled. So we have 3 arrows. 1, deprotonation, abstraction of the proton from the backside, breaking of the bond between alpha carbon and alpha hydrogen to form the pi bond, and dissociation or expulsion of the leaving group. The new pi bond will be between carbons 1 and 2, 1 and 2, and not between 1 and 6 over here. This pathway is not followed. Double bond between carbons 1 and 6 would have led to less highly substituted non-Zaitsev product with only 3 groups on a double bond. Zaitsev product happens to be tetra-substituted because I have 1, 2, 3, 4 hydrogen atoms attached to the double bond. So I can designate this as Zaitsev tetra-substituted. Alkene. Again, when you have more than 1 alpha hydrogen, in this case we have 3 alpha hydrogens, 1, 2, and 3. Of those 3, only 2 are axial and antiperiplanar to the chloride leaving group. Deprotonate the more highly substituted position, in this case tertiary hydrogen and not the secondary hydrogen. This will give you Zaitsev product. Let's take a look at 2 examples of substituted cyclohexanes bearing iodo leaving group, and the only difference between them is thus the neighboring alkyl substituent is either cis or trans to the leaving group. Let's focus on the cis arrangement. So here let's number it 1 through 6. Let's draw the chair conformation. Carbon number 1, 2, 3, 4, 5, and 6. Carbon number 1 is pointing down. Equatorial bond will be up. Iodo group is up, which will happen to be equatorial, and hydrogen atom is down, which is axial. I do not have to go any further because I see that my leaving group is equatorial, and therefore I need to flip the chair before I consider the elimination pathway. So again, number 1 consideration, leaving group has to be in axial position. We flip the chair, number the ring in the same fashion, counterclockwise, 1, 2, 3, 4, 5, and 6. Carbon number 1 is pointing up, so my axial bond is up, equatorial down. Go to carbon number 1, iodo is up, and therefore hydrogen is down. Circle the leaving group, confirm that it is indeed axial, and then draw the remaining substituents. Carbon number 2 is pointing down, axial bond is down, equatorial is up. We're looking at carbon number 2, methyl group is up, and therefore hydrogen is down. CH3 up, hydrogen down. Carbon number 5, hydrogen up, CH3 group down. That's over here. And carbon number 6 is unsubstituted. Now that we have all of the substituents correctly positioned in their right places, let's go ahead and ensure that we have drawn and labeled all alpha hydrogens. This is the carbon atom in question, my alkyl halide. Next door at carbon number 2, I already have axial hydrogen. Carbon number 6 has axial hydrogen and equatorial hydrogen. We have 2 alpha carbons with 3 hydrogen atoms. Here I have a tertiary alpha carbon with a tertiary and therefore more acidic hydrogen. And here I have secondary alpha carbon also with 1 axial alpha hydrogen. Since both pathways are potentially plausible, since I have 2 alpha hydrogens, both axial and antiperiplanar relative to the leaving group, I can potentially eliminate either one of them. In this case, when you consider the product of E2 elimination, you will follow the Zaitsev rule and eliminate the more acidic hydrogen. My base alkoxide will abstract the more acidic tertiary hydrogen from the backside. Bond between alpha carbon and alpha hydrogen will break and collapse toward the incipient pi bond between carbons 1 and 2, and the leaving group will be expelled. 3 arrows. 1, we're abstracting the hydrogen from the backside. Second arrow, center to center. The bond between carbon and hydrogen is being broken. Those 2 electrons will serve to make the pi bond between carbons 1 and 2, and the leaving group is expelled. Our product, therefore, will have a double bond between carbons 1 and 2. 1, 2, 3. Double bond, and fill in the missing groups. I have a methyl group at carbon number 2. Notice that I will not draw either wedged nor hashed bond because now this carbon is trigonal planar and therefore all 3 groups connected to that carbon are in the same plane. Carbon number 1, the leaving group was lost. I have hydrogen atom remaining. Carbon number 5 has hydrogen pointing up and methyl group pointing down since we did not do anything at carbon number 5. I will designate this product as the Zaitsev trisubstituted alkene. Zaitsev because of the 2 alpha hydrogens that were coaxial and antiperiplanar, axial and antiperiplanar to the leaving group, I eliminated the more highly substituted, the more acidic one. Trisubstituted because I have 3 non-hydrogen groups connected to the alkene. I have methyl group, CH2 group, and CH2 group. So trisubstituted. Now let's consider elimination pathway of HI from a similar compound, and the only difference is that the leaving group and the adjacent substituent are trans to each other. So I will go ahead, draw the chair conformation. I will number the carbon atoms in the same fashion, counterclockwise, 1, 2, 5, and 6. My substituents are as follows. Carbon number 1 is pointing down, so axial bond down and equatorial up. Leaving group iodo is pointing down, hence it is in axial position, and hydrogen is up. This is my reacting conformation because the leaving group is axial. At the carbon next door, I have axial and equatorial bonds. Carbon number 2 has a methyl group pointing up and therefore hydrogen is down. And carbon number 5 has hydrogen up and methyl group down. Axial down, that's my CH3, and equatorial up, that's hydrogen. I circled the leaving group. I confirmed that it is occupying an axial orientation position, and then I will draw my alpha hydrogens. I have 1 tertiary hydrogen at carbon number 2, it is equatorial, so it will not be eliminated. Carbon number 6 has both axial and equatorial hydrogen atoms. This is my secondary carbon atom. Of the 3 alpha hydrogens, 1, 2, 3, there is only one that's axial and antiperiplanar to the leaving group, and in this case it happens to be the less highly substituted axial hydrogen. My mechanism, therefore, will involve deprotonation from the less highly substituted secondary carbon backside. The bond between carbon and hydrogen will be broken, and 2 electrons will go center to form the pi bond, and the leaving group will be expelled. In this case, my pi bond will be between carbons 1 and 6. 1, 2, 3, 4, 5, and 6 will fill in the missing pieces. At carbon number 2, I have methyl group pointing up. That carbon is still sp3 hybridized, and therefore we use the wedged bond, so the orientation pointing up does not change. Leaving group at carbon number 1 is gone. I only have a hydrogen atom. Carbon number 6 has 2 hydrogen atoms. One was eliminated. I still have one left. And here I have unchanged arrangement of methyl group hydrogen pointing up and methyl group pointing down. My alkene is non-Zaitsev product because it is disubstituted. I only have 2 carbon atoms connected to the alkene, so I will designate this as non-Zaitsev disubstituted alkene. Let's take a look at the expression for the rate for each reaction. I will go ahead and label one alkyl halide as A and the other one as B. Expression for the rate law for the top reaction will be proportionality constant times the concentration of A times the concentration of the base sodium ethoxide. Same goes for the reaction below. Rate will be proportionality constant times the concentration of alkyl halide and concentration of the base. In each case, we can say that if we double the concentration of one component, the rate will also double. If we double the concentration of each of the components, the reaction rate will quadruple. Just to review, we recognize that each reaction will follow the E2 mechanism because we look at the reaction conditions. We have alcoholic solvent, some heat, and we have a strong or concentrated base where the base is greater than 0.5 molar concentration. In such case, when we have E2 elimination from substituted cyclohexanes, we draw the chair conformation. The reacting conformation will be one in which the leaving group is axial. That's true in both cases. And then we'll find the most acidic axial and antiperiplanar hydrogen. If possible, the Zaitsev product will prevail. If not possible, owing to the requirement for the antiperiplanar arrangement, the product will be less highly substituted non-Zaitsev alkene.